Hey, thank you for joining us for the second video in chapter 5 where we're talking about stereochemistry. Let me set some do not disturb on. And we last time talked about the categorization or classification of different types of isomers, which stereoisomers is one type of those. And then we talked about some differences between diastereomers and enantiomers. And how the enantiomers are mirror images that are not superimposable or identical, right? And then diastereomers are stereoisomers, but they're not mirror images. That's not how they're related, right? And then we talked about chiral centers, which I can't emphasize how important this is, this point, right? That it's about 4 different carbon that has 4 different groups. Maybe I'll even highlight this. Right, that's a chiral center, and we talked about examples of chiral centers, and actually it just occurred to me as I was thinking about that video that I could have actually just, since I'm doing screen recording, I could have just done this to show you, whoops, what I meant about the enantiomers. So these are 2 mirror images of each other, and hopefully you could see that, and yet they're not the same, they're not identical, right? Like they're not superimposable when you try to superimpose one over on top of the other. So these are mirror images of each other, and these are enantiomers of each other, right? And so that was kind of silly and sort of old guy moment for me to not realize I could just use the iPad camera on the iPad screen to just show you what I meant with the actual objects. But again, I really highly recommend you use your own molecular model kit to study and sort of do a hands-on learning with a lot of these things. Anyway, today in this video we want to talk about the physical properties that arise from the chirality. Or remember, being chiral means like you have an enantiomer. If you have an enantiomer, you're chiral. So chiral molecules rotate light. Now, non-chiral molecules like say H2O, water, also rotate light too, but when you have a bunch of non-chiral molecules like water on top of each other, right, like they just randomly rotate the light in random directions all together, and so the end result is when light goes through the water, they don't get bent. The light doesn't get bent in any particular direction. But if you have a pure substance, pure chiral molecules, and no other contamination, those chiral molecules can, because they're handed, right, because of their handedness, they can rotate the light in a particular direction, and that's what we call optical rotation. And when you measure that, often it's depicted like this with the Greek letter alpha, and often you might see the subscript and superscript together with it. That just means that this was taken at 25 degrees Celsius. D stands for the sodium light or lamp source. That's what that means, and that's where the source of the light that was bent. And then this in turn is defined like this: alpha over L times C. And the idea is that, like, if you measure the rotation, like how many degrees your chiral substance bends the light when the light goes through your chiral substance, that's the measured rotation. You can measure this in terms of like a degree, right? Like angle, right? And then the thing about that is that rotation or degree of rotation changes depending on how concentrated your solution might be, or how long how long of a distance your light had to travel through. We typically put these samples in a device called a cell. We put the solution that we're measuring in a cell, and then we put that in an optical rotation measuring device, right? And so that's what's going to happen. And so for that reason, we need to standardize it, right? Because maybe one person's optical rotation instrument might be different than the other, and so you need to account for that. And so for that reason, this is going to be your cell length, and it's measured usually in decimeters for whatever reason. Don't ask me why. And this is the concentration. And what this does is it allows you to standardize any measurements, so that regardless of what optical rotation measuring device you might be using, whether and then regardless of the size of your cell, or regardless of the concentration of your sample, we can all compare the same thing because we normalized it based on those concentration. And this is often measured in grams per milliliter. Okay, and this normalized value is called specific rotation. Okay, and it's often measured on a device called a polarimeter. That's the optical rotation measurement device, polarimeter. Okay. And so once you make calculate for specific rotation, now these things can be compared between different labs. Okay, and often this is really helpful in determining optical purity, which in turn often is used to determine things like how much of a particular chiral substance you might have, or what kind of chiral substance you might have. Often that's used a lot in the food industry, especially in the sugar industry or some sort of carbohydrate industry, because depending on which type of sugar you have, whether it's fructose or glucose, they rotate the light. Those are all chiral molecules. They rotate the light in different amounts, and so that's what they take advantage of to determine what kind of sugar, how much you have of it, and stuff like that. Now, I hope this is intuitive to you, that enantiomers rotate the light in the opposite directions by the exact same amount if the concentration is the same, because their handedness is the opposite, right? And we like to have some terminology for those, so we know which we don't have to say right-handed compound or left-handed compound, right? So the word for sort of right-handed compound or molecule is dextrorotatory. Often abbreviated D isomer. What that means is that this compound or stereoisomer or enantiomer would rotate the light in the positive direction, which is defined as the clockwise direction. And then the opposite of that is called levorotatory, or L isomer. Is rotates the light in counterclockwise direction. Okay. And that's of course determined experimentally. And so what, as we mentioned, what you do with the polarimeter measurement is you typically want to determine the optical purity, which is the same as enantiomeric excess. And the reason is, if you have excess of one enantiomer, it should bend the light in one direction, and that is related to, directly correlated to the optical rotation that you measure. And so what is how is this defined mathematically? It's the observed specific rotation divided by the pure enantiomers optical rotation times 100%. So if you have 100% pure material on your hand, that would be, these two values would be the same, so therefore you have 100% optical purity. That means it's 100% pure enantiomer. You don't have any of the other enantiomer contaminating it. Okay, this is really the same as the absolute value of one isomer minus the other one, the difference, divided by the total of the two isomers in a particular sample. And this might sound kind of complicated, but what this just means is, if you have, say, 50-50 of D and L isomers, they bend the light in both opposite directions, so they kind of cancel out. In fact, if you plug that in, if this value is the same as that, that's a 0 over some number is 0%. And then we'll think about some, and that's called the racemate. And we'll think about situations where the two amounts might differ by some amount. Okay, and so racemate is a racemic mixture where the optical purity is 0. And again, in this context, we're not talking about purity in terms of like being contaminated with some totally unrelated stuff, but we're talking about just the enantiomers ratio. If you have 1-to-1 mixture of enantiomers, you have a racemate or racemic mixtures. There is no optical activity. As in, you don't see the light being bent in any direction. In reality, it gets bent, but they're bent in both, in opposite directions by the same amount. In other words, they cancel each other. And that's why you don't see any bending of light. So the specific rotation you would observe should be 0 at that point. Now, so if what if 80% of the sample is dextrorotatory isomer and the 20% of the sample is levorotatory? What is the optical purity of the sample? Well, this is something maybe we'd like to think about in class. Okay, and the crux of the matter is, would you be able to determine the optical composition from the optical purity? And that's an example that we want to visit in class as well, to solve these problems together. So see you then.